I guess the key thing is I just want to try and really lay out the energy challenge to you. Try to convince you that we need to take a whole systems approach if we're going to tackle the energy challenge effectively. Then I'm going to try and explain why, at least from an engineer's perspective, we feel that there's a lot of uncertainty, complexity in our energy systems, and that's growing year on year. And the importance of flexibility in all its forms in energy systems is growing and is very important. And then really, I suppose, I then want to say, so if we're going to tackle that energy challenge and deal with that uncertainty and complexity, then there's a real need for AI and data science in this energy space. And so I guess that's one of the main reasons for coming here is to see if we can start a discussion and see if I can enthuse you to come and work in the energy domain if you're not already. I'm going to describe briefly some example projects that I think hopefully illustrate the kind of concepts that I'm talking about. So I'm going to tell you a little bit about some energy storage research that we're doing, some work that Miriam, who is here in the audience, my colleague, is leading on electric vehicles and vehicle-to-grid technology with Nissan and National Grid. I'm going to say a little bit about digital twins. We're doing some work building digital twins of energy systems, and I know that's of interest to the Alan Turing Institute as well. And then a little bit about how we've started to think about cybersecurity in energy systems. And a project that we've just launched a couple of weeks ago is the SuperGen Energy Networks Hub, funded by EPSRC. And we've got our first advisory board meeting next week. Alan Turing Institute are on that advisory board. And this hub is there to do core research, but also to try and grow the energy networks community and welcome in people from the AI and data science community. So we can maybe touch on that and discuss whether we think that's useful or interesting. Okay, so just trying to set the scene in energy, and apologies to people who are experts in this space already and know this, but we've got UK and global targets around decarbonising our energy system. And we've had this UK target for some time of reducing our greenhouse gas emissions by 80% by 2050. And that was when really the main aim was to maintain global warming to within 2 degrees C. And now with the latest IPCC reports, you can see that really now we're being told we need to maintain global warming to within 1.5 degrees C. So we're going to have to do more than that, and we're going to have to do it faster. So it's a huge challenge. The other thing to put alongside this is that the UN Sustainable Development Goals also have lots of goals and aims around energy and decarbonisation. And a problem here, if you like, something that could be seen as being in tension with decarbonising our energy systems, is to recognise that globally there are still 1 billion people without access to electricity and 3 billion without access to clean fuels for cooking. So although we're trying to decarbonise our energy systems, if you like, in Europe and North America, there's a huge challenge because globally we're trying to provide energy to many, many more people around the world. And if we don't do that in a low carbon way at the outset, then we're going to hit some serious problems. So the UN SDG, or Sustainable Development Goal number 7, is around affordable and clean energy. So really, I suppose one of the things I wanted to say and stress, first of all, is to stress the point that the energy challenge that I'm referring to is an incredibly broad challenge. It's really inclusive. Anybody can work in it, really, pretty much from any discipline. So we work with computer scientists, mathematicians, anthropologists, economists, lawyers, geothermal engineers, all sorts of different people. And really, this energy challenge really does go from the molecular level, when we're designing new energy materials and energy storage devices, right through to the design of energy markets. It goes from things like the application of artificial intelligence through to aspects relating to fuel poverty. We've still got millions of people in the UK living in fuel poverty, for example. We need to design new energy policies, new interventions to get to where we need to get to. And then we've also got things like how do we make best use of cloud computing to help facilitate some of the breakthroughs that we need to make. And we've got grids, networks that need to be re-envisaged, reimagined and re-engineered. But as we do that, if we're not careful, we're going to introduce vulnerabilities around cybersecurity. So we need to think about that. And of course, energy systems underpin transport systems, food systems, water systems, and they impact on air quality, not least relating to transport. So it's a really big, broad, interdependent system. So it's very difficult, very challenging, but also very open, lots of things to do, lots of ways to make your name, I guess. So if we look at the UK energy sector at the moment, the way I would characterize it is that it's fragmented. So although I've just told you that the energy system is a big interdependent system, the way that it's run, the way that it's governed, the way that the industry is set up is actually, if you like, the opposite to that. It's very fragmented. People work in silos. The industry work, you have companies who not only look at electricity and nothing else, but they only look after the wires and the transformers. They don't buy or sell energy, and they don't own generation. Then there are companies who only own generation. Then there are companies that only buy and sell. And that's just within electricity. Then we've got gas, we've got transport, we've got all these different places. And government is also fragmented. So the government tend to look at energy in silos as well. And also in academia, very often in academia, people look at a very small piece of the energy puzzle and don't really collaborate across disciplines. So one of the things we're trying to do is break down all of those silos and start to work in a more multidisciplinary, collaborative way. Now, carbon is still too high in our energy systems, as I'm sure you know. There has been some breakthroughs in electricity, but there's still a lot of work left to do in heat and transport in particular. I'm going to show you a graph that I hope really illustrates that in a very visual way. Energy costs are too high for some sectors of society in the UK, but also it's worth knowing that many families spend more money on fizzy drinks in a week than they do on electricity. So there's a real difference in different parts of society. And at the moment, security of supply is adequate for most customers, but there are some threats out there. So one of the things we're interested in is, as climate change progresses, how can we make our energy systems resilient to that? There's a lot of work done in energy systems research where people say, well, if we decarbonize the energy system, we can mitigate climate change and then everything will be fine. But I think there's a growing realization that climate change is here now and that the climate system has a big lag in it. So even if we decarbonized everything tomorrow, we would still see progressive climate change over the coming years. So we need to start to think about how to make our energy systems robust and how to adapt them to climate change. And as I mentioned before, cybersecurity is a potential threat out there that could reduce security of supply. So this is the graph really that I would like to refer to try and make this point that it's not all about electricity. A lot of people, when they talk about energy, actually they've got this idea in their mind that it's just electricity. Okay, it's more than that, and hopefully this shows it. So this red trace here, this is gigawatt hours per day of energy consumption in the UK, by the way. And this red trace is electricity consumption. The blue trace is a proxy for heat demand by looking at our gas consumption. And then this grey trace here is transport fuels. So what you can see is that electricity is around 20–25% of the UK's total energy consumption. But there's been a bit of an obsession with electricity. We've done a lot of work there to try and decarbonize it, make our grids smart. And what that's led to over about probably 15 years of effort is that we've managed to decarbonize about 30% of that red trace there through the use of renewable energy. So really, we've done about 30% of about 20% of our energy system in 15 years. And you think about the challenge we've got to get to at least 80% reduction by 2050. So we've got to tackle these other parts of the energy mix, and we've got to think about the energy mix as this whole system, because these three traces are actually highly interconnected and are becoming more and more interconnected as well. Of course, if you imagine electric vehicles eating away at this transport fuel and those being charged from an electricity system, as one example. Okay, so the next few slides are a little bit wordy, so bear with me, but I just want to make a few points here. So I'm trying to make the case now that we need AI and data science. We need the AI and data science community to join us in tackling the energy challenge, okay? We need to grow the energy community. There are not enough people in this space. When we advertise for postdoc RAs in energy, it's very, very difficult to get people with the right skills. There's a massive skills shortage. But also we need different people coming into this space with different skills. The current energy system analytical tools that we have in industry and academia are no longer fit for purpose because of this growth in decentralization, the growth in uncertainty, the growth in complexity. We need different tools. We need different mathematical techniques, different data science techniques to help us deal with the problems that we've got. What characterises us at the moment in this energy space as having lots of data now that we didn't used to have, but we're not really using it effectively. We are developing data analytical techniques and trying to use them through things like machine learning, but we're doing that as engineers. And I don't want to insult engineers here, really, as an engineer myself, but we're not specialists. We're not core specialists in AI and data science. We're reading the literature, we're talking to people, and then we're trying to take those skills and apply them to the energy domain with some success. But my view is that if we were working more closely with the real experts in this field, we'd do better and we'd do better faster. So that's what I want to try and do here. We are developing AI techniques and applying them, things like fuzzy control, neural nets, evolutionary techniques like cuckoo search, for example, embedding some of those within multi-agent systems. But again, we're doing it from an engineer's perspective. We do build digital twins, and I'll show you one of those in a moment, of the energy system, but I wonder whether we're really exploiting those fully and really getting the full benefits. And so there are questions there, I suppose, that we would like to pose to some to experts like yourselves, which is, are we using these tools appropriately? Are we using the right tools for the right tasks? Because for me, when I have an engineering challenge and I look at the plethora of AI techniques that I could use, how do I know which ones or which one is the right one for this particular type of problem? And I would say engineers often read a little bit and then just have a go. I think we could be a little bit more thoughtful with some help. And I suppose the other thing as well is if we use an AI technique or a data science technique, it gives us some insights, it gives us some answers, but are we really interpreting those results and those answers properly as well would be another question. So I guess finally we need specialists and we need to upskill the energy community and we need the energy community to grow. So just to pick up on the phrases that I used before about uncertainty and complexity and the need for flexibility. So as we decarbonize our energy systems, we're adding more and more renewable energy into them. That's adding more and more fluctuating or variable energy sources. We're also bringing in a lot of decentralization. So we're moving from an old system where we might have had, say, 50 generating plants, power stations, that are all centrally controlled, all with a fuel that you can put more fuel on or put less fuel in to control the output. Pretty much all the energy was going in one direction, from the producers to the consumers. We're moving from that picture to millions of small generators that are driven by weather patterns, for example, plugged into the grid in all sorts of different places. Highly variable output, highly geographically dispersed, and no real way to understand how to control or manage that in a coherent way. So we need new techniques to allow us to do that. The multi-vector idea that I was talking to you about also brings a lot of complexity. So the fact that the heat networks, the gas networks, the electricity networks, and the transport networks are all interconnected and all interdependent, and we see more and more that energy and money and data is flowing between all those vectors and sectors, that makes the problem a lot more complex. If you also then step back and think that each one of those different vectors, those different energy systems that are interconnected and interdependent, have very different physical makeups, different phenomena that drives how they behave, very different time constants for how things change, for example, then that makes the modeling and the analysis of that big, complex, interdependent system very, very difficult. On the other side, if you're going to, let's say you even manage to build a fantastic model of all of that, and you can look at all the data, and then you want to control that energy system, if you can imagine, that energy system has multiple constraints and multiple objectives, many, many of those. And so that, coupled with uncertainty about the consumption, production of resources and how you move it around the energy system, means that you've got some very, very difficult operational tasks and very, very difficult planning tasks. How do you plan? How do you predict what's happening in an energy system like that? How do you invest in it? How do you control it in real time? Very difficult, needs new techniques. Often the analytical techniques that people have used in the past fail to converge or fail to provide useful answers. So we need new tools. And the other thing is that where we need to go now, because of planning constraints, because of capital constraints, and because of the uncertainty, there's a general consensus that we need to solve a lot of these problems through control and flexibility, through things like demand-side response, energy storage, and fast control, rather than investing in bigger physical plant. Okay? So it's in the past, we've tended to build bigger and bigger grids and leave them to be passive, whereas really that doesn't work anymore now in such a decentralized, highly flexible system. So instead of investing in more and more copper and big plant, we want to invest in data analytics, control systems, to make sure that we can keep the lights on, keep people warm, whilst decarbonizing that system. The other thing is that there's a big push towards democratization of energy systems as well as decarbonization. So that means involving people and organizations in the way the energy system operates. So that means that us here, we can basically own our own mini power station on our roof or in our back garden. We can also control our energy consumption in any way we might want to for commercial benefit or for environmental benefit. And that means that we've now got millions of participants in the energy system who are driven maybe not necessarily by what economists might call rational drivers. So how do you model and understand and predict the way that humans will behave and interact with the energy system now and in the medium and long-term future? How can we do that? We need help with that. The other thing is that just purely modeling techniques become very, very difficult. The computational intensity explodes very, very quickly when you're trying to model a multi-vector energy system with temporal and spatial detail in it. And in the past, people have tended to give up and just build very high-level models with most of that temporal and spatial detail taken out of it, and a lot of the physics that describes the actual behavior taken out of it too. But what we want to do is say, no, we do need to build those complex models, but how can we make them computationally tractable? So we need help with that. And then this final point about cyber attacks. Okay, so hopefully now I've convinced you of a few things, maybe not, but I'll try to convince you the energy challenge is vast. It needs people like you in it, and a whole systems approach is the right way to go. So this is the National Centre for Energy Systems Integration that Darren referred to earlier, and we lead this from Newcastle University. And the idea here is that we're trying to work for 5 years with these universities to try and tackle this whole systems energy challenge. And we've got a very diverse team, as I said to you before, across social sciences, mathematical sciences and engineering. We've got the National Innovation Centre for Data, for example, at Newcastle University working with us here as well. Here are some of our government, international and national partners that we work with. And as well as trying to take a multidisciplinary approach, we're also trying to take a bottom-up approach. So we're working on full-scale, real-world demonstrators of energy systems, taking the data from those real energy systems and then trying to use them to calibrate and validate models that we use, and then move those up through the complexity levels and scale. And we are just over 2 years into this project. And this project has a flexible fund that it can procure additional work from the community to come and work with the centre and tackle these challenges. And some of you may know Chris Dent, who I know is a fellow here, and he works with us on this national centre as well. So if you wanted to talk about that. So just a little idea to try and illustrate one very small piece of what we mean by the interdependence between different energy systems and why that might be useful but need better understanding. So if we think we've got an electricity network on the left-hand side here and a gas network on the right-hand side. Now at the moment, the interactions between those systems is fairly small, okay? This is one separate company running here and one separate company running here, a separate market here and a separate market here. The only real coupling at the moment typically would be that the gas network might feed a combined heat and power unit that might produce electricity that is then injected into this grid. Now what we see is because decarbonisation in electricity networks has been faster than in gas networks, we're hitting times when these wind farms here can't export their energy into the electrical network because the electrical network is congested or full, if you like, it can't cope. And so we're spending millions of pounds at the moment either switching off these wind farms or asking them to reduce their power output because we can't deal with it, okay? In the meantime, over on the gas side, we've got utilization levels of this system of about 20 to 30%, okay? But because these systems are run in silos, people aren't really coupling the two. And because people tend to say, well, I've got a problem in the electrical network, so I should solve it in the electrical network, they start saying, well, let's build a big electrochemical energy storage system here. And then we can let the wind farm output and we'll charge a big battery. But I guess as we all know, those batteries are very expensive, their lifetimes are quite short, and that might not always be the right thing to do. What you could do instead is you could drive an electrolyzer with the excess energy from the wind farm, produce hydrogen, and then you could blend that hydrogen into the gas grid. You could move that hydrogen around the gas grid, and then you could either combust it for heating, or you could put it into a hydrogen fuel cell vehicle somewhere else, okay? What you've done there is you've maintained the revenue for this wind farm. You have decarbonised the gas grid to a certain extent, and you've also managed to make sure that when you've invested all this money to build these wind farms, you're getting all the low carbon energy from them. Because the key thing here is renewable generators are zero marginal cost generators. So once you've built them, to produce another megawatt hour doesn't cost you anything. It's not like a coal-fired power station where if you produce another megawatt hour, you've got to burn a megawatt hour's worth of fuel, coal, which has a cost, okay? So even though you lose some of this energy in the conversion process, at the moment you're paying to just throw it away, yeah? And this is a kind of strange outcome that we get due to the fact that things are siloized, they're not integrated, all right? So that's just one example of how taking a whole systems approach, hopefully we can get further, faster in decarbonising energy systems. Okay, so I'm going to tell you a little bit now, some examples of some of the work that we're doing. And I've picked these examples of things where we think we need help from the AI and data science community to do better, faster. So we do work on energy storage at Newcastle with lots of partners from around the UK and internationally. And the way that we tend to look at it is we start off with what services do we think the energy storage needs to provide to the energy system. And because energy storage at the moment is relatively expensive, what we look to do is stack multiple services from a single energy storage system to provide, to maximize the revenue and therefore value from that energy storage system. Now the problem in doing that obviously is that each one of those services takes up energy capacity, and also each one of the services there's uncertainty about when you will be asked to provide the service and for how long and how much energy you need to provide. And so that sets up immediately a really interesting challenge of how do you control the state of charge of the energy storage system. If you get caught where the battery is too full, you've got a problem. You can't charge it anymore. If you get caught where the energy storage system has too low a state of charge, then you can't provide the service. And you might be contractually obliged to do it, but even so, you still want to stack multiple contracts with multiple people to maximize the revenue. So how do you do that? And once you know what those multiple services are, how do you size that energy storage system, and how do you pick what technology to use? And then also you need to look at end-to-end modeling of the energy storage system, right from the molecules through to the markets and the services. Why? Well, one reason would be if by earning £1,000 by providing a service to the grid, I do £2,000 worth of degradation damage to my energy storage system, then I've actually made a loss. So I need to understand molecular degradation mechanisms as well as markets and services to the energy system so that I can make sensible choices about what to do with that provision. And we do that through building grid-scale facilities at the university and also by building full-scale grid-connected systems with industry. And then more recently, we've started to build cloud-based platforms, predominantly with Siemens actually at the moment, because we're envisaging a future where somebody might own a few thousand energy storage systems that have different technologies playing in different markets, geographically dispersed across Europe, and they might want to coordinate and manage those through the cloud. Collect all the data, do the data analytics, make those sensible choices about how to maximize revenue and protect their asset base. So this is the kind of thing we do. And these are the kind of laboratories that we build. So we have big energy storage test beds at Newcastle that are connected to the 11 kV network in Newcastle. And we can control and integrate those different storage devices. These here are Second Life EV batteries from Nissan Leafs. So we're looking at, could you take them out of the cars and use them after they're no longer useful in the vehicle? And then we have high performance computing where we build real-time models and simulations of the energy system. And then we're able to couple those models in real time with the physical grid and the physical energy system. And we can have the physical system and the model interacting in real time with each other, which is very useful. Okay, and yeah, I guess this slide really is just showing that then we overlay on top of that this cloud computing platform called MindSphere. And obviously there's no reason for it to be MindSphere. It's just an illustration of one cloud computing platform. And the idea is that you can write apps that can run in this open platform to try and deliver some of the things we're talking about. So just keeping an eye on time. So these are some of the full-scale, grid-scale rather, energy storage projects that we've worked on. So this one here is a 10 megawatt-hour energy storage system in Leighton Buzzard. This is a 5 megawatt-hour system in the northeast of England. And this was the very first grid-scale storage project we did with a utility, which was just under a megawatt-hour in storage. But we've built all the models and developed the control algorithms for those. But again, they're fairly simple control algorithms, and I think we could do more and do better. So if we look at how we tackle this, we use decision trees to try to understand how to combine essential technical services from the energy storage system with commercial services so that we think we can try to maximize the revenue, but also make sure we can still deliver. And we do this by using real service data taken from the utility companies, real energy system data, and we run lots of simulations using Monte Carlo techniques to try and get to a kind of probabilistic view here of what's going to happen. Because one of the things is, if you build an energy storage system and you connect it to the grid, there's quite a lot of uncertainty about how many times are you going to be asked to provide certain services, how much and for how long, and therefore what kind of revenue will you get from that storage device, and also how long will it last before it's so degraded it can't deliver any more services. So this kind of thing gives you a set of cumulative probability distributions for different aspects that are important. So things like the state of charge that the energy storage system will find itself in, how many cycles it's likely to experience. And in this case here, this is one example of where the storage system is overcoming a network constraint here and also providing earning revenue through providing something called STORE, or short-term operating reserve. So it's a combination of two services using historical data and trying to guess, or make an estimate rather, of what that energy storage system will experience when it's in operation and what kind of revenue here it might produce, because that revenue is uncertain. Okay, so here's some work. This is just referring to what I said to you about an end-to-end modeling system. So here we worked with Imperial College, who developed a material science model of a lithium-ion battery that had degradation mechanisms embedded in it. We had Oxford University build a detailed power converter module. This is the converter that couples those lithium-ion cells to the grid. And then at Newcastle, we built a grid model and simulated the services and the markets. And then we were able to see how to maximize revenue here, whilst also being able to understand what we were doing to the materials. So we could see degradation at the same time as we were providing a service, and we could even see the temperature of the individual semiconductors in the power electronic bridge. So this was a really interesting piece of work. Most of these pieces of work that I'm referring to are published as well in journal papers. So if people want to ask me later, I can provide the links to the detail, because I realize I'm skipping through this fairly quickly. So there's another project here that's just starting, which is called E4 Future. And this is the project that Miriam here leads. And this is a £10 million project. You can see the partners, Nissan, National Grid, UK Power Networks, for example. And the idea here is that this project is going to explore how we could have vehicle-to-grid systems out there, how they would be operated, how to make them cyber secure. Can they really provide a kind of virtual battery for the UK? And you might not need to build full-scale big energy storage systems if you're able to access potentially millions of electric vehicles plugged in to dispatch, charge and discharge in a coordinated way. So the project in a nutshell, and Miriam can tell you a lot more about this than me, is that we would have lots of these different vehicles, and I think we're looking at fleet vehicles, are we, in the first instance, and how those fleets of vehicles, when plugged in, can dispatch into this grid here to help balance against variability through wind and solar power. And the idea is that there's an aggregator in the middle, a cloud platform that E.ON are going to provide and develop with us, that's going to allow you to look at what's required by the grid and then get that in a highly decentralized way. Obviously, the key there is you've got to make sure that you still leave enough state of charge in all of those vehicles for people to go on and be able to do their onward journey. Just quickly touching on another aspect here. So this is about energy storage again, but it talks a little bit more about how we've done some work with development of a digital twin. I don't think we realized it was a digital twin when we first started doing it, but when Mark Girolami came to see it, he said, you've built a digital twin of an energy system. And I said, oh yes, of course we have. So let's try it out. So enhanced frequency response is a brand new market that was created not very long ago by National Grid. And they created this market specifically for energy storage. They wanted to procure very fast response from energy storage to help them control frequency of the power system. Controlling frequency of the power system is becoming more and more difficult as we add more and more renewable energy, because it introduces variability, but it also reduces system inertia. And system inertia is the thing that helps keep frequency stable. So there's a kind of double whammy effect going on as we decarbonize. So they put out a profile like this and said, this is the service that we will procure. We're open for bids, but we need it from energy storage. And the response has to be within 1 second of a frequency deviation. So it rules out a lot of conventional technology that couldn't respond that fast. And the contracts have been given for this now, and the projects are in existence. But at the time we did this work, the market had just been created, and industry was saying to us, how are we going to do this? We don't know if our technology or our control algorithms can really deliver it. So how can we test that and understand it? So we took a lot of data. National Grid made frequency data available second by second for 2 years. We took that data and we started to analyze it. And here we can see the actual frequency and the standard deviation of the frequency over those 2 years. So we could start to understand how the grid was living and breathing and what kind of requirements would be placed on energy storage to provide this enhanced frequency response. We were able to look at, there were 2 types of service you could provide, a wide service and a narrow service. And we could start to look at low frequency events, high frequency events, and how they were distributed. Because obviously that's important, because when there's a high frequency event, you're going to absorb energy into your battery, and therefore your state of charge is going to go up. And if there's a low frequency event, then you're going to export energy from the battery to try and bump up the frequency. So we looked at all that data, and then we translated that into how many events would there be, and what duration of events would there be, and then also from that, what kind of state of charge range would you see different types of energy storage have? So we then built a model in our real-time digital simulator that could run in real time and pretend to be the national grid with all that variable frequency and inertia. And then we were able to attach to that a real energy storage system in physical hardware, connect the model and the hardware together in real time, and then run 2 years worth of events and test whether the energy storage system could deliver within a second in the right way. And then we were able to share that in a journal paper and with industry and help people get the confidence to bid for this market. And that's now happening in the real world. So that was a really nice use of a digital twin, and it allowed us to develop something and analyze it very quickly, actually. Now, another piece of work that we did that's a bit further out there that might be of interest is we did a project with these university partners a couple of years ago called the Autonomic power system. And the idea here was that we might be able to have something called self-star network operation and control. So the idea was that meant self-organizing, self-managing, self-healing, self-protecting energy system through using artificial intelligence techniques. And the concept really was that in the energy system, the goals change with time. That gives us different objectives, and it's no longer appropriate to have one algorithm like we have now. We usually have simple analytical algorithms, a single one that manages the energy system all the time. And the idea here was, as uncertainty and complexity grows, no one algorithm will be the best performing algorithm. So you need a basket of algorithms, and then you need to know which one to deploy at any one time. And also we said we should be able to dynamically split the network up into different zones to allow us to control them more effectively, because we felt we couldn't try and control the whole system in one go, because this level of uncertainty and complexity would mean that would be computationally intractable. But not to have static zones, to have dynamically changing zones that you're merging and splitting based on what's happening in the network. And we developed some artificial intelligence techniques to automatically do the zone definition, and also we developed a machine learning technique that would be able to pick the most appropriate algorithm from a basket of algorithms. And we were able to show, and both of these bits of work are published in journal papers, we were able to show that dynamic zone definition was better than static, and we were also able to show that an algorithm selector could outperform quite significantly the best algorithm if it was there working all the time. So we showed that there was value in doing this. One other piece of work that we did in this space was to look at self-organizing control architectures that would allow us to make the energy system more robust to cyber attacks. So we developed a self-organizing architecture that could change the levels of hierarchy in it, how flat it was, how hierarchical it was, how centralized it was, by promoting agents in the hierarchy, demoting agents in the hierarchy, instantiating dormant agents, putting other agents to sleep, and reconfiguring when we were under cyber attack. And we tested this on a low voltage network with lots of customers, and we envisaged that the point of vulnerability was the smart meter in the home. So we imagined that somebody had managed to hack into some smart meters and then start to put denial of service attacks into that grid. And we could see that very quickly you could crash the voltage control system for this part of the grid, which would cause the customers to be tripped and lose supply. And what we were able to show through looking at this self-organizing architecture and lots of different attacks, burst attacks, continuous attacks, attacks that weren't very sophisticated, ones that were adaptive and would chase and move around as we adapted. And in simple terms, we could see that through using this self-organizing technique, we could maintain the voltages within limits when it would crash without, by looking at message response times and message congestion in the network, using that to give us an indication that we were under a denial of service attack, and then reconfigure the architecture. But again, as I say, this is engineers having a go at this, and I'm sure if you looked at it, you'd tell us where we could do it better, where maybe we've made some mistakes. So finally, I was going to just mention very briefly this SuperGen Energy Networks Hub that I mentioned earlier. This is an EPSRC project that's just started. The Alan Turing Institute are a partner or on the advisory board. It involves these universities here. And the idea is that, again, we're going to take a multi-vector approach to energy networks. This diagram here shows you the way the work packages are constructed. So we've got the verticals of the vectors: electricity, heat and cooling, and gas. And then we've got cross-cutting strands of ICT and data, policy and society, markets and regulation, and risk and uncertainty. And we're going to try to work around this area. We've got a big initiative to make sure that we're supporting early career researchers. We've also been asked to act as a beacon for equality, diversity, and inclusion on behalf of EPSRC. So we'll be pushing very hard to make sure we're open and welcoming to everybody into this community. And we also have a quite generous, flexible research fund that we can use to procure additional work, get new partners and new skills to come and work with us. So we've got hub activities, which are about connecting, convening, and promoting and growing the community. So I hope I'm doing something towards that aim today. And then we've got a technical core research program, which you can see here, where first of all, we're going to try and understand multi-vector energy networks better. Then we're going to try and shape them and look at different architectures you can see here. And then we're going to try and challenge them by looking at major societal shifts, major climate change impacts, and big technological shifts and changes, maybe like superconductivity or the effects maybe of cybersecurity deterioration. So these are many of the partners, as you can see here. It's Alan Turing. And we're kicking off our advisory board on Thursday next week in the Crystal Building in London. So that's really everything I wanted to say. But you can see in summary there, many challenges. A whole systems approach is needed. We're trying to deal with uncertainty and complexity and decentralization. We need new ways of working. We need new skills. And we'd love to collaborate with you, if possible, on this big challenge. Thank you very much.